gonna take a look at multiple of these happening, right? So let's see if I can get this simulation to work. Huh? Can I finish it here? All right. So what is a diffraction grating? So we need to understand what a diffraction grating is first, right? So watch this here. Right. So a diffraction grating is this thing here. So imagine you have this piece of glass, right? And on that piece of glass, let's say that piece of glass is like 1 centimeter, right? In that glass, there are, let's say, 1,000 little cuts. So you're taking a glass cutter and you're making 1,000 parallel cuts. So you might something like that, right? So and every cut is a slit. So look at your ruler. Look at 1 centimeter. Right? Look at your ruler, that's 1 centimeter. And imagine you have a cut there. A cut is like a space. So you have a line and you have a little cut and you have a little space like that. Imagine you have 1,000 of those in that little 1 centimeter. That is a diffraction created. Right? So you have like 1,000 slits in 1 little centimeter. Right? That's a diffraction created. What's the separation between those slits? Really small, right? Right. So that pattern that will be observed when light passes through that grating is called a diffraction pattern or diffraction grating pattern. That's okay? So imagine interference happening about 1,000 times and it will produce a pattern. Right? Very similar like that, like that. All right? So watch this here. So let's take this diffraction grating here. Right now, move. So I can move that. Right? So we have the laser. Right now, let's move it. I can't move anything. Oh, sorry. I can't move it like that. So I'm going to put the grating in place. Watch this here. So I'm going to put the grating in place. And watch what happens. That pattern you observe there is a diffraction pattern. Watch it again. I'm removing the grating. Right? And I'm going to place the grating now in front of the laser. All right, Aaron? I'm going to put the grating in front of the laser. And you have that pattern being formed. Every one of those patterns, let's see that thing. Every one of those lines the pattern. So instead of seeing bright fringes on this screen, instead of seeing bright fringes on that screen, what you will see is green, 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 green. You will see green and that. Green and nothing in the middle. It will look something like that. So really and truly is the sharp green, then real light green, and sharp green again. Yeah, the V for the space as well. By a particular angle, of course. Huh? Right, so let's take a look at what will happen. I am going to change it now to a different wavelength. Let's see if we could go up to like, not change it to, right, it went to yellow there. Okay, I'll take it all the way up to red. Can I mix it, boy? Nope. Put it in place, pattern. Right? I am going to adjust the number of gratings, number of lines in every millimeter. Right? I am going to decrease it a little bit. And by decreasing it, I have more fringes. I have more fringes on the screen. You see that? But the official name here is no longer fringes. It's called orders. Right? If you look closely, this is in middle order. Order 0. Next state is order 1. Here is order 1. In fact, I shouldn't say they're equally spaced, Nikolai. They're not equally spaced. Right? I'll show you how to work out the angle. So you have order 1, and here you have order 2. So if I were to choose red light with a diffraction grating of 296 per millimeter Soraya, I will end up with 2 orders. All right? If I were to drop it further, I could even squeeze in 1 more order. Did I squeeze in the next order? Yeah, I did. Right. Right? I was able to squeeze in a next order. Right? Let's change the wavelength. And as I decrease the wavelength, I'm able to fit more orders in. That's okay? So the smaller the wavelength, the more orders you'll observe. But what you're observing there as well is there's a maximum number of orders. When it was red, the maximum number of orders was 2. All right? Let's see if we can get a smaller simulation to see it again, right? I want to show you what happened with the waves. Right? I want to show you what will happen if they mix if it's more than one wavelength. That's allowing us to mix the wavelength. Okay, but that's how to look on the screen. You see the little red dots? Let's change the green. See the green dots? Huh? Let's change the blue. See the blue dots? That's how it will look, right? So if I change the grating, right? If I adjust the grating, you'll see you'll be able to get more orders. So that's basically what you're seeing. Blue light and white in between. That's okay? That's basically how it will look, right? Huh? Yeah, raw HG I'm trying to get you one with white. White will give you raw HG. You see, everything we're using here is monochromatic, one wavelength alone. Let's put it in color. Right? If I were to mix it now, if I were to mix it with white light, you will not see one color. You will see a mixture of colors, right? I'm just trying to find a simulation how to do that. Hold on. For 1 second. All right, so what's this here? Let's say I gave you something like this, right? It's not the best, right? Not the best, but what I want to point out here is a few things, right? All the little white spaces, there, those are the little cuts in the glass, right? So the light is going to go through there, undergo diffraction, and then interfere, right? As it undergoes the interference, this is the pattern being observed, right? The M, this here, represents the central bright, or the central bright fixture, central order. That's okay? Now, that's not the first order, that's the central, right? That's the one that goes to undeviated. So the colors here will match all the colors here. All right? But all the others now, right? The colors are split up. So here, this is your first order, this is your first order. This is second order, second order. And well, they didn't try the third order underneath, right? But that is your third order. So if you have light, in this case, it appears that this green light, right? Why the same monochromatic? Anyway, let's pretend that white light. That white light was split up into all the colors. You're seeing that? So pretend it's white, right? Let's say this is white light. When the white light goes through, here will be white because that's undeviated. So nothing will happen there. And then it was split up into Roy, right? Red, orange, yellow, green, blue, indigo, violet, right? So the light now is split up into Roy G-bit. Roy G-bit. All right? So it will split up into Roy G-bit, right? Right, George? Yeah? All right, so let's take a look at the notes on this now, right? I'm not finding the next one, but that's basically the image. Right. Let's take a look at diffraction of light. Right. So diffraction is not normally observed since the wavelength of light is very small. Right. By the way, you have to learn this. Huh? You have to learn that red is around 700 nanometers and violet is around 400. Right. So you should have an idea if it gets in yellow or red or green or what. Right. All the time. Right, so you should know violet is like 400, red is like 700, and be able to average in between. will be close to flash. Yeah. And the rest will be in between. In between, yeah. So right, right? So diffraction only become pronounced when the width of the gap is comparable to the wavelength of the wave. Right, Saraya? What must happen again? What is something? Pay attention, please, right? The wavelength has to be comparable to the spacing. So therefore, you cannot observe diffraction, Saraya. You cannot observe diffraction if the spacing is large, right? If you have a small wavelength, you have to have a small spacing. Okay? Right, so a diffraction grating. Here we have a quick simulation of a lab, right? Of the things that you would do to obtain the angles and the grating and adjust the spacing and thing, right? Huh? Yeah. So as the slit, is the same thing that we're going to do now. As the slit width is decreased, a diffraction pattern is observed. What's the diffraction pattern again? If it's red light, what you'll see? Red space, red space, red space, red space, right? And you will see equal number of orders on either side of the center. Okay? It's observed on either side. Pattern consists of a central bright bands and alternate light and dark, right? But you will also notice that they are equal intensity. They all equally bright. It's like in interference, it goes from bright to a little dark, to a little less bright, and so on, right? I'll show you the graph just now. So what page to be 35. Right? I have to give you two diagrams there. I'll send that pic, but let's go here. Angular positions of the minima are given by A sine theta is equal to n lambda. So here's what you need. What you see earlier. Separation between one of the slits is E. Right? So that separation there is E. The wavelength coming, the light, the wavelength coming in is lambda. Very similar to what we did last week. Right? But here's our change now. When the wave passes through here, right, the one that undeviated is your order 0. Right? Then the first order will deviate. This is your first order. It will deviate by an angle theta 1. And it will equally spaced on both sides. Here is also theta 1. Are you okay with that? So n represents the order. A represents the separation of one of the slits. We can note these things, huh? Right? Because they were here even in the calculations. And lambda is the wavelength of the light coming in. Right? I'll call it out again. A is the separation of one of the slits. Underline the word 1. Write it down. What everybody write down the formula. You'll need it. A 1 slit. Right? A is the separation or the spacing of one slit. Lambda is the wavelength of the monochromatic light. Of the light coming in. Lambda don't say monochromatic. Lambda is the wavelength of the light coming in. Oh, Kazaria, not here. Right? Theta is the angle. Theta is the angle between the central bright or the order 0. Theta is the angle between the central bright or order 0 and the order you're trying to find. This is the formula for diffraction grating. You want to see diffraction grating, you use A sine theta is equal to n lambda. Some people use D sine theta equal to n lambda. N is the order. N is the order. Right? So theta 1 will be the angle between n is 0 and n is 1. Theta 2 will be this angle here. Watch it. It'll be that entire angle. So theta 2 will be the angle between n is 0 and n is 2. Theta 3 will be the angle between n is 0 and n is 3. What are you doing there? Right? If you have an order 2 on the left side, you also have an order 2 on the right side. Okay? It's symmetric about the order of 0. Whatever you have on the left, you'll always have on the right. Well, the hardest thing in the questions is to find A. A is the number. A is the separation of one of the slips. All right? All right. So what's your goal? Right? Because I want to make sure you'll get it, right? Everything else you can just read. Right. So what you see? Right. Same thing we're talking about. We have light coming in. We have, this is one of these patients. You have your central bright, that n is equal to 0. Then you have your first order, n is 1. This is theta 1. You have the same thing here. You have the same thing here, it is theta 1. All right? Then you have n equal to 2. This angle from here to here is a theta 2. This angle from here to here is your theta 2. All right? And everything here is A is equal to A sine theta is equal to n lambda. Right. We know what each term is, right? As I said, there's a maximum number of orders that's possible. Okay? And to work out the maximum number of orders, we need to remember something, right? Maximum number of orders. What's the largest value for theta? All right, it's 90, right? If you have a screen here, right? The largest angle that you could observe there is anything smaller than 90. Because anything bigger than 90, you wouldn't be able to observe it, right? But anything smaller than 90, you'll be able to observe it here, right? Once it goes beyond 90, you will not be able to observe it. So therefore, the maximum number of orders occur when theta is 90. So if I put 90 in here, sine 90 is what? 1. So you'll get A is equal to n lambda. So the maximum number of orders is A over lambda. That's the maximum number of orders, right? A is equal to, n is equal to A on lambda. And I want to point out something here. Let's just say, Sarai, since he eaten. Right? Saraya, suppose when you work out this whole formula here, you end up with 3.9. Right? Pardon me, sir? The max number of orders occur when theta is 90. Because what's the largest angle you could read off on a screen? So imagine this. 10, 20, 30, 40, 50, 60, 70, 80. But what will happen when we reach 90? It will be here. Will this ray, you'll be able to read it off there? No. So the largest is 90. Technically, it's just below 90. Right? But we use it approximate as 90. Yeah. Soraya, suppose you work out this whole thing, right? And you saw that your maximum order is 3.9. Then how much orders on each side? 3 or 4? right? The answer is 3 because based on the calculation, 4 impossible, right? And these orders are whole numbers only. So what they're saying here is that the maximum number is equal to 3. So you always round down because if you end up with 4, if you write 4, then 4 will be a much bigger angle on this. Okay? Pardon me? Yeah, it's called rounded down. So you round down, right? So when you're working it out, you always round down. Okay? Nice. How do we handle A now? Let's say we have something like this. Let's say we have 1,000 lines in 1 millimeter. And you want to find A. Right? What is A? A is equal to 1 line. A is the spacing of 1 line in meters. Okay? So 1,000 lines in 1 millimeter is 1 line in 1/1,000 millimeters. And you want to convert that to meters after, right? How are you doing now? That's okay? You just convert meters to 10 to the minus. Sorry, milli to 10 to the minus 3. Right? So now you have 1 line in 1/1,000 by that, which is how much? 1 by 10 to the minus 6. So one spacing, one spacing. Remember, you have thousands of these, right? One spacing is 1 by 10 to the minus 6 meters. Okay, so that's the A value you're using. All right. So to find A, right? 2 things you do. The first thing you do, you find for 1 line, and then you convert to meters. All right. Those are your 2 steps in finding A. Right. This out. Type this out. It's on the phone, right? So I should take it. Yeah. Thing is, if I give my question, you go and get right. Because the wish of the people. You gotta see that. Are you playing game now? I see different items. I'll check the cash. All right, so you want to be able to do calculations like this, right? Ready? Let us see what we could. Right, here's a slight problem that is happening in questions like this, right? You have to figure out when to use A sine theta equal to n lambda and when to use y is equal to z lambda on A. Right? St. George looking like he's bored there. George, add a little excitement to your life here, George. George, when you use this formula, close, something else. Right. Right, so this one here is used for diffraction gratings, right? Thousands of slits in a millimeter, right? This was interference, right? When it has 2 slits. Okay? That was similar pattern, but the graph that missing, I give all of this graph. I'll give it. Right, the intensities are the same. One, the intensities here are the same, the intensity for the next is the same. All right, let's see if we can tackle a couple of all right, watch this one here. All right, so let's do this one together. Take a little read. So here we have a diffraction grating, right? And the diffraction grating is 4.55 by 10 to the 5 lines per meter. So this one was nice. They gave it to you in meters. And it's used to examine the light from a glowing gas. The first order violet. So what they give you there? 11.8. What they give you for 11.8? So that's theta 1. So when n is 1, theta 1 is 11.8. And then when n is 1 to red, it's 15.8. So they want us now to go backwards and solve for lambda. Basically. So you're coming back to the same formula now, and you're making lambda the subject in this case. Please remember, people who are doing pure math something, make sure you calculate in degrees, right? Right? Make sure it's in degrees. And Monday we finish up? Yeah, Monday we finish up. Right? So let's try to make with lambda the subject in each one and work it out, right? How do you know n is 1 earlier? Let's just say first one. Right, so remember you had to find here. So let us find A. Don't forget to find A, right? Nope, that's not A. That's how many lines in 1 meter. A is always for one line. Right? So this is saying 4.55 by 10 to the 5 lines in 1 meter. We need to find for one line. That'll be A. So it's 4.55 by 10 to the 5. Yeah. How much is that? 2.2? All right, 2.2 by 10 to the minus 6. Right? Remember, I told you A is very small. So it can't be 10 to the 5. The diffraction pattern will not be observed, right? And then rearrange the formula and solve for lambda. Lambda is what? Lambda is A sine theta all over n. Right? A is 2.2. A is 2.2 by 10 to the minus 6. So I get 4.5 by sine, that's not right. By sine 11.8 all over 1. That'll be the wavelength of violet. And we know violet is how much? Around 400, right? How much you got? What's the exact value you got for this one? 4.7 by 10 to the minus 7. So that's why it's important to know about red and blue, right? To know about the wavelengths. One line, are they okay? 4.5. .5 by 10 to the minus 7. Violet is around 400 something. Around there. Remember that the differentiate. The lowest n is 400. Right, fine for red. That's part of the question. So our next part. Find both wavelengths. I just found violet for you. Find red. 6 by 10 to the minus 7. So we can Nikas to finish it here. How much you got, Nikas? Yeah. 5. Me? 5 point how much? 5.98. Yeah. 5.98 by 10 to the minus 7. Nice. Last part. Let's take a look at the last part. So last part, right? Right. So here, with aid of calculation, determine what happens at the angle 54.8. So you have to plug in, both colors. For both colors, you have to figure. For both colors, you have to figure out what's happening at 54.8. So, and you know A, no, we don't know. We had to find for it. We know theta, we know lambda. So we had to solve for n, right? So work it out and see. Make n the subject of the formula now. Yeah? Sorry? For the first part, you had to do both of them. Oh, yeah. Yeah, you had to do it twice. 11.8 was for violet, and we got 4.5 by 10 to the minus 7. Change the angle and then find for red. Part 2, the way to think about it. And Chabi, and you have theta and you have lambda. So you can define for n. Yeah, and see what happens. Yes, so you have to find n in both cases. So. You have to find n in both cases and then see what will happen. Sorry. Why don't try it again, just make it n is subject. How much formulas relate to diffraction grating? One, only one. So n is equal to a sine theta and lambda. Right, so plug in 54.8 for both of them. Red wavelength and the violet wavelength. And tell me what happened.
Is exactly
3.99. Correct?
Yeah.
Exactly true, so
I got 3.2.
3.99. Yeah, 3.2 something, right? Let's pretend it's 3.01, right? Let's pretend it's 3.01, right? That's the red here. And now we'll talk violet.
That was the red.
Also, what was 3.0001?
That's for
Right. I just squeezed in 3.01. So it's 3.000 something, right? I just pretended it's one because I want to show you something. Oh, violet was the wavelength. 4.5. So you got 3.99. Right, question. Divide. For red, be careful to be sure. For red, we got 3.01. Right? 3.00001, something like that, right? And for violet, we got 3.99. So, based on what I showed you here, what is the order of red? 3. So the order of red is 3. What's the order of violet? Still 3. Right? So it's not 4. You don't ever round up, right? What does that mean? I use the example. Oh yeah. Yeah. What's the board be 3? So what's the difference here? One was 4 now. Yeah. So it's right? Oh, if you get 4 point something. Yeah, what is 4? And the other one's 4. Then one on 4, one on 3. Right, so what does that mean? What does that mean, Aria? Both of them are 3. When you work out violet, you get 3 at 54.8. When you work out red, you get 3 at 54.8. What does that mean? What's that? So they would have the same wavelength. What is happening at 54.8? So let's pretend here is 54.8. What is happening here? Anybody? What is happening at 54.8? Right? The third order is up to both of them. So therefore, getting closer. So they both overlap. Right? So red overlaps violet at 54.8. All the other times they will separate. Look at order 1. At order 1, you observe violet at 11.8. At order 2, sorry, at order 1 for violet, it happened at 11.8. At order 1 for red, it happened at 15.8. So they will separate. But now at order 3, both of them exist at the same angle. Huh? How they could?
Overlap, they don't have the same.
At that angle, they appear to meet, and then they overlap it. Right? At that particular angle. Because remember, the further, they are not even, as I was showing you. They are not even. So here to here even, but here and here not even. So there might be points for certain types of light where they come close together, certain wavelengths of light. That's okay? Right? But normally, what will happen? Normally, one will be at one particular order, next will be at next order. Okay? That's how it will normally happen. Everybody okay with that? So, what we learn here? Number 1, we learned from the question that in order for us to find A, we have to find the thickness of one line in meters. Number 2, the next thing we learned here is that, well, we're using this formula all the time, right? Once the diffraction grating, we use it A sine theta and lambda. And the third thing we learned here is that there's a possibility that different wavelengths could overlap. All right? Yes. Right? What that possibly also means that probably order 4 to X. Let's just check it and see now. Check and see the maximum number of order for check and see the maximum number of order for violet. Just work it out. Divide A by lambda. And tell me what's the maximum number of orders. What's the maximum number of orders for? 4? Right. For violet is 4. Violet is 4. And check for red. You round up, you round down, right? So violet was how much? Violet is 5? 3. And red? 4, right? So it means that violet stopped at 3 there. But red overlapped into 4. Two more. Try this one here. 2 more. Just on next one, you'll get it. Huh? Wait, remember? Go back in the chat, please. Go back in the chat when I send that message. Right? I was first screenshot here. Oh yeah, try this one here. Try this here, come on. Yes, none. Yeah, none. Right, so this one they give you with wavelengths. They give you the order and they want you to find when this is split spacing. What do you want? What symbol you want? A, theta, and all that. Sure? They want the set spacing. Oh, okay, right? And then they want the angular positions. What do you want after that? Angular position. Angular. Theta, right? So part 1, they want A. Part 2, they want theta. And part 3, well, so you put it like 1 mark. Oh, yeah. Okay, when you have 2 minutes to work this out. Oh, yeah, my next one after. Nano is 10 to the minus 9, yeah? Nano is 10 to the minus 9. All right, let's see how it's going now. So to find E, that's part one. That would be 600. Oh, by the way, remember it was 600. Sorry, it was 6,001 centimeter. Right? So you have to convert to meters. So A would have been 1 by 10 to the minus 2, that's in meters, divided by 6,000. How much is that? 1.67 by 10 to the minus. Right? I don't want to say all the time, but most of the time the answer is around minus 6. Huh? Of course, sir. Of course, sir. Right, so that was A. Now you want to get theta. I like to just make theta the subject one time, right? So theta will be sine inverse n lambda on A. All right. They said order 2. So that will be 2. Right, that will be 2 by 656.3 by 10 to the minus 9 all over A. A is 1.67 by 10 to the minus 6. And the angle is how much?
0.23.
0. Yeah, it should be something like that. That's something better. 51.8 degrees. Got there. So let me show you the degrees. See that? DOR. 51.8. Well, yeah, don't forget the sign up for the crash courses, please. Right? Right, use the link, yeah? And what you got for the next one, Leo? You still working on that? Sorry? Quick question, right? Ignore the formula a little bit. Ignore the formula a little bit, right? The larger the wavelength, what you reckon I come to the angle? So what's it good? So the 656.3. What was the angle? And 486.1. What was the angle? Right. What is diffraction again? The smaller the opening, when compared to the wavelength, the greater is the diffraction. Okay? So look at it closely there. The wavelength is what? Right? The wavelength is 656 nanometers. So when you compare this to the opening compared to this one, right? This opening is much smaller than this. You see that? When the wavelength bigger, right, the angle will be larger. Right? And the reason is, right? And the reason is the opening is now much smaller than the wavelength. Right? Once the opening is smaller than the wavelength, you will have more diffraction. So the angles will be larger. Right? When the opening, like for example, 486, right? When the opening is not as small when compared to the wavelength, you'll have less diffraction. All right? So if you remember the simulation we did, the smaller I made the opening, right? You recognize the left patterns here because the angles are larger, right? So you can play on with the simulation and you'll see the same thing. But for now, smaller the wavelength, the smaller the angle. Bigger the wavelength, bigger the angle. Right. Part 3 is what? Take the difference between the two angles. The smaller the spacing when compared to the wavelength, the bigger the diffraction, so the bigger the angle. Right? But in this case, you can watch it. The bigger the wavelength is, bigger the angle. That's easy thing to remember. Right. Here's what I'm saying, right? Oh, hold on to part 3. I want to share on board. Hold on to part 2 and I'll show you part 3. Right, here's what I'm saying. If the wavelength, I'm not changing the size of the opening, right? Right? If you remember, right? Remember in Form 5, when we did diffraction, right? We said the smaller this opening, the more it's spreading. Yeah? Right. So, if I were to reduce the wavelength, right? When I compare this opening to this wavelength, this is looking a little bigger than this, and so the diffraction wouldn't be as pronounced. But if the wavelength is comparable, or this is smaller than this, right? Then you will have greater dispersion. Okay? So if I am not changing this, if I'm not changing the opening staying the same, the bigger wavelength given me, greater spreading, so theta is more. And the smaller wavelength given me, less spreading. Okay? So the bigger the wavelength, the more spreading. Closer the wavelength, the less. Right. Here's what they're asking us now. You all just worked out theta 2n, correct? So you worked out theta 2 for order 2. And the question said, what is the angular separation between the orders? And that's what it said. So you had to add them, right? So the question said for the angular separation between the orders. So these are the orders. So the angular separation is all here. Okay? If you minus them. Oh, wait. So sorry. What do you ask for?
Since this have two wavelengths, we have to multiply it, right?
Okay, I got this. What do you ask for again? I lost the question. For the two lines. Oh, sorry about that.
Yeah.
But if they ask for these two, you add them. But they ask for between the two lines. Okay, yeah. I was wrong. Right? So for one wavelength, order 2 was here. For the next wavelength, order 2 was here. So yes, you minus them. Right? I was now going to point out if you minus this and this, you'll get 0. Yeah. Sorry about that. So I forgot. It was two different wavelengths. All right. One more, and then I'll give you a small break and we read up on the I after, right? Oh wait, no break. You forget the message. That's the last one. If we want to do come back in time. All right, last one. Last one. Right, because this sign up. No, this last one here. Look at this here. Right, I don't really want to work it out. In fact, I want to work them out. Last one here. Take a little read. Right? Because you will help us with part 2. And then Nalia will help. No, Aria will help. No, Aria, Alina. Alina will help us with the next one. So read the first one, and I want you to tell me what's the formula we use. Read the first one. Huh? The one with? Yeah, the one on top. This is part 1 here. This is 1, and this is 2. So what are we using, or what are we doing in 1? Yeah, Aryan. So Aryan said y is equal to t lambda. Why? Because what? Right? Because the keyword there, have a keyword there.
Yes.
Pair of slits. And it's 2 slits. Y is t lambda. Right? Next one is what? Alina. What formula is it for number 2? Which one? Right? A sine theta equals n lambda. What's the keyword there? Well, 2 words. Fraction. All right. So the keyword in number 2 is this, what words? And the keywords here is pair. Okay, that? So you have to know which one to use. All right. If you need a break, take a 5 minutes. If not, work out this. 5 minutes, huh? And I'm going to tell you to correct this. Yes. Online, if you need it, you can take a 5 minutes. If not, you can go ahead and do it one time. It's 7:55, huh? No, it's 2 minutes late. Hurry up, Paul, yeah. We have to read out the I after, right? Yep, last question, and then we just read out the I and be done. Cash didn't do any work today. Some of them more than that. Check in against number. Right, Nalia, the talking is finished? Okay, good. Right, Nalia, for part one, what are we doing again? So I asked the topic. Yes. Nalia, so I'll do the next one. Just talk about it, Nalia. That's not formula. Y is equal to D lambda on 8. Arian, are you done? One second, Arian. Huh? For the first part. What is the wavelength? Nanometers? They want the answer in nanometers. Why is the wavelength? Sorry. Why is it different between the splits? Y is 1.4 by 10 to the minus 3. A is how much? A is 0.2 nanometers, right? Sorry, millimeters, yeah. 0.2 by 10 to the minus 3 is A. Amanda got 560. Yeah. I divide by 0.5. Huh? You tell me. Why is it? You don't need to see it. Why is what? Why is it nanometers? Sorry. Why is 1.44 millimeters, right? You got up 560. Oh, yeah. Yeah, I can put everything to meters. Nanometers. Nano, because this I convert back to nano. Nano is 10 to the minus 9. Anybody else get for 560? Nanometers there, so it's 560 by 10 to the minus 9. Huh? Why? Why we can't put it in the first place? Because we work in meters, all the quantities in meters.
You're right, you must be one.
Yeah, so what you might have gotten was 5.6 by 10 to the minus 7.
Yeah.
Right, and then convert in nano. Nano is minus 9. So you go to the right one.
I get 5.6 by 10 to minus 7.
Question says nanometers.
Oh.
Next one. You get you? How much you get? So your next one, part 2, you get 560. All right. Can't reach it. What? Sir. Oh, part 2 is the second question.
Yeah.
They want the number of rulings per millimeter. I just want the board. Yeah. Right? Because the number of rulings per millimeter are a little different. But that's not it. Nope. You gotta convert, you gotta do the reverse. You gotta take A and get a number of rulings. I'll show you. Yeah, you do the reverse here. Right, so watch this here. Bing, bada, bing. The angle between the two first order. So the angle between the two first order. The angle between the two first order on either side is 27.7. Yeah, divided by 2. And the wavelength is how much? The wavelength is 5.89 by 10 to the minus 7. So they want us to get the number of spectra obtained, right? So they want to get, okay, I remember that also. Right? So when you reach here, we're using A sine theta is equal to n lambda. They don't want A. They don't want for 1. They want how many, millimeter or meter? Millimeter. I mean, not millimeter. But we have to get A first. A is equal to n lambda over n is 1. Lambda is 5.89 by 10 to the minus 7 over sine theta. Theta is not this. Right? Yeah, and it's a first order? No, it's not first. It's between the first two. Right? Between the first order here. Right? So I think it's between the first order. Right? And the theta is not 27.7, because 27.7 is the angle between two orders. We are divided by 2. How much is this? Sorry. When you work out this out, no, give me the whole answer. Pardon me, ma'am. Because remember, theta is here. Right? But this is 2 theta. $2.46. Right. So what is this? This is one line. So one line is equal to 246 by 10 to the minus 6 meters. So let's convert this to millimeters. So one line is how much millimeters? Multiply by 1,000, right? So it's 2.46 by 10 to the minus 3. Right? Right? You don't see this either? Right? Right. So this is 1 meter. No, this is one line. This is one line in meters, one line in millimeters. So now I'm going to find how much in 1 millimeter. So I'm going to divide this by 2.46 by 10 to the minus 3. I do the same thing here. Right? If I divide this by itself, I'll get 1 millimeter and do the same thing here. I'm just making sure I'm showing. Right? So I convert one line meters, I convert it to millimeters, and then I find for 1 millimeter. How much is this? How much? 406.5 lines in a millimeter. You know what I do? Devish? Right? I try to break it down nicely. I follow Antonia. So one line is this thickness. So, but that's in meters. So I form one line in millimeters. Right? So now I want to find for 1 millimeter. So I divide by this. That will be 1, right? So I divide by itself and divide by itself. And I get 1 millimeter is this. Right? If you had done it, you would have went here and then divided. And the last part is what? Number of orders. Right. So they want n. So what are you really asking for in the last one, Nikila? What are you asking for in the last one? Shall we read it all the time, Nikila? They ask for the maximum number of orders. Okay? So that's A over lambda. How much you all got? So by the actually total number of orders, so they kind of ask for the max, right? They just create the difference. Put it back in class. What you got? 4.2. So therefore the number of orders on each side is. All right. So you have 4 on each side. All right. Right. We have one more thing to do to read up. It's the I, right? Some things you know already, but I'll just go to it, right? Well, you can read it for home. Yeah, right. Yeah. All right, so let's take a look at the I. Any questions online? Oh, that's cool. You have 11 notes to web forward, right? Well, they come all day and practice. Let's mess it up. Guys, this is not A. So I watch A is equal to. This is it. Remember, A is for how much? A is the spacing of one line. All right. Quickly, let's run through lenses, right? So you have to know my Sophia and how to fix some things, right? You can always read it too, but let's run through. Are you ready? Right, you have to know about lenses and you have to remember the lens maker formula. 1 on F is 1 on U plus 1 on F. Right, you have a little bit trickier part, but we'll do some, when I do questions on that, I'll do this stuff. Right, lenses. We have two types of lenses, converging and divergent. The more important one is the convergent. You have your focal point, your focal length. You have your light rays. What is called a dotted line? Right? What is called a dotted line? Oh wait, it's not zooming in. We're going over this thing where it's thick. That's not as thick as thick. That's not. Give me 1 minute. Give me 1 second. Right. What is called that dotted line there by the focal point? The principal axis perpendicular to that. The focal plane. Right? Right, here's your divergent. Remember for divergent lens, right? To get the focal point, you extrapolate it backwards, right? Right, you have the optical center, principal axis, principal focus for divergent. Focal plane is the plane that I showed you all. Right, Vikas? Right, magnification formula there. Are you okay with that? Tequila, you okay with that there? What you do it? Pay attention, please. Right, you have magnification, and now you have something new. It's called power. Power is 1 on focal length, Soraya. Right? So 1 on focal length is your power. Power is in diopter. I think it's spelled wrong. Huh?
So that's like how they
how they measure your lens and your eyes. Right? One slight problem is that power, the focal length must be in meters. Right? When you're working on power. Right? Converging lens have a positive power, that's not T, that's positive. Diverging lens have a negative power. Alright? Then you have your lens maker equation. Right? 1 on F is equal to 1 on U plus 1 on V. Right? V is the image distance. Just in case you all forgot what that is. You have your lens. You have your object here. From here to here is your image distance. The image, sorry. U is your object distance. From here to here is your image distance. Alright? 1 on U plus 1 on V is 1 on F. Right? If V is positive, then it's a real image. If V is negative, it's a virtual image. Where are virtual images generally found? Alright, on the same side as the object. Yeah. Right? On the same side as the object. Yeah, that's going to be it. All right, and then you have a few examples here to look at. You can plug it in and look at that. Something that we need to know, we need to be able to label up the eye. Label it here. Right, but here's the problem. Right, Olia, you need to read up on short-sightedness. Right, I don't know what happens to this table here, but you have to read up on short-sightedness and long-sightedness, right? How you fix short-sightedness? Concave lens. Right, and long-sightedness is convex lenses, right? Make sure you can draw it, make sure you can explain, and please read out the rest, right? Right, read out the rest. And I think we should be done with module 2. Right, we did intensity. We did air. All right, last thing. I'll do the part papers like in class or something, right? But I don't think we reach to the air. Here. Like here in range of thing. This here. Read this homework, right? Alright, online. Right, for homework, just read up on the air, right? So that's the end of module 2. If you all have exams and you want to come in and do past paper, they come in, right? Just message before to make sure I get it. Huh? Be here later, well, I'll be here. Alright, online. That's it. You can log out, right? Bye. Amanda, tomorrow. No, you're the Amanda. Submit. Yeah.
Okay, go back. Because like I said, no, I have this pure item cover like myself. Look at this. I this pure item cover. Stress. I no, I just don't come. I feel I check that all I see. Yeah, I just put on a oh my god. Yes, sorry, my this time,
Hey, what's the I leave this thing here for?